Okay, so let's go ahead and get started. We are going to basically finish up our section on probability, or our chapter on probability today. So we're really just going to cover 5.2, finish covering 5.2. We'll get into and we'll finish section 5.3 and then we'll be done. So we're just going to not do the simulation on 5.6. We'll kind of pick up with some of the simulation as we move through the remaining chapters. So that's not a big deal. So we'll finish up chapter 5 today. And then when we get back to school on Wednesday, we'll start in on chapter 6. Okay, so we talked the other day about probability. What are the two rules that we know for probability? Have to equal 1, the sum. The sum of the probabilities must equal 1, that's right. What else do we know? Help us out here. What else do we know about probabilities or possibly even percent? If you want to look at it in that. What do you know about percent as well? So it has to add up to be 1 or it has to add up to be 100. That's correct. What else do we know about things like that? It can't be less than 0 or greater than 1, right? We cannot have it less than 0 or greater than 1. But it can be 1 and it can be 0, right? So it can be those two things. That's perfectly fine. All right. And so those are the two cardinal rules. How do I find probability? Let's say that I wanted to roll a single dice, right? I want to roll a single 6-sided dice, and I want to know what is the probability of getting a 5? 1 out of 6. And why did you say that? That's exactly right. There's 6 outcomes, right? There's 6 outcomes on our dice. Y'all looking up here? We don't need to be on the computers just yet. So go ahead and look up here. If we have a single die, right? There's 6 sides on that die, and there's only one way to get a 5, right? So that's the root. That's the way that we get our probabilities. And if we say that it's a 1 in 6 chance, which I think is 0.167, something like that. I don't remember what the decimal value is off the top of my head. If I change it into a decimal value, that would be the relative frequency. That's it. That would be the relative frequency of getting that 5, right? Of rolling a 5, correct? Very good. Now we moved past that. We started talking at the end of the class about the addition rule. And we had something that we had to consider when we think about it, our addition rule. And that was disjoint or mutually exclusive events. And I don't think I made it clear enough, so I want to backtrack just for a minute. When we talk about our addition rule as well as our multiplication rule today, those are rules that we apply when we have what we call compound events going on. So more than one thing is going on, more than me just rolling that single dice. Right? Remember, we've tried to figure out what the probability was of rolling a die and flipping a coin, right? So we had 2 things going on in that case, and we end up putting a rule to it. So when we think about something that's not a single event, if I have compound events, then we move into our addition and multiplication rules. What did it mean for something to be mutually exclusive or disjoint? They have nothing in common. They have no outcomes in common, right? We can represent that with our Venn diagram up here. And then we have our rule that we talk about, the general addition rule. The general addition rule is here. We wrote this down last time that said if we have 2 events, and I want to know whether it's this, what's the probability of this or that, right? We can just come up with a general rule by taking the probability of event E, adding it to the probability of event F, and if they do have things in common, then we subtract off the part that's common. Remember, we don't want to double count certain items. All right, and so we can just really think of our addition rule as being this general addition rule, because we can, if we don't have anything in common, then we wouldn't have anything to subtract off. So we can kind of just summarize it in this one particular rule. Now, one of the things that's easy for us to talk about probabilities is if we can somehow relate our probabilities in a what we call a contingency table, really just a two-way table. And in this particular example of our contingency table that I've got up here, we're trying to relate two different categories. So what I have are a university conducted a survey of 375 undergraduate students regarding satisfaction with the student government. So we have the different classifications for each of the students that are at the university, freshman, sophomore, junior, senior, and then whether or not they're satisfied, neutral, or not satisfied. So we have these two categories that we are adding up. Now, what do we call that kind of a table right there? Has a special name. What do we call it? Starts with an F. It's the frequency table. That's right. It's a frequency table. And everything that's in white here, not the margins, but everything that's in white right there is just a table like we're used to seeing. And and that's highlighted in yellow for us here. If I go through and I add up all of the columns and I add up all of the rows, you can see that each of those is summed in what we call a margin. The marginal distribution is kind of what we call it. All right, so each of these values down here underneath the columns would be the sum of how many freshmen answered. So 96 freshmen answered, 83 sophomores, and so forth. And then moving to the right, if we're talking about rows, we have how many total answered that they were satisfied, how many total answered that they were neutral, right? So we're just adding up either the rows or the columns. And this one particular cell down here in the very bottom right-hand corner would be the total of either the row, either the column or the row. So if you added up the total row, it would equal 375. If you added up the total column, it would equal 375. And from this, it's easy, it's a special way for us to be able to kind of talk about probability because we can talk about their relative frequency, okay? Their relative frequency. So here I have some examples that we want to look at. And it says, if a survey participant is selected at random, what is the probability that he or she is satisfied? So probability of satisfied. Well, how would we find that? That's a single event, right? We just want to know how many people thought that they were satisfied. So how would I figure out what is the probability that I find somebody at random that answered that they were satisfied? How many total people answered that they were satisfied? 233, right? So 233 people out of a total of 375 people, right? Because we're asking how many people answered that they were satisfied. If I put all of these into a hat and just drew them out, all right, and we would know that that ends up being 0.621. So it's a 62% chance that I'm going to pick somebody who was satisfied, right? 62% chance, okay? And I can just find these by looking at the table. Makes it kind of easy, right? I don't have to do anything special. How about the next one? If a survey participant is selected at random, what is the probability that that participant, that he or she is a junior? Now remember, we're going to practice by writing capital P, and we're writing the event that we are looking for. What is the probability that I randomly pick somebody that's a junior? How many people are juniors?
93.
93 out of how many people available?
375.
So 93 divided by 375 ends up being 0.248. So it's a 25% chance that I pick somebody who was a junior. And that, again, is an individual event, right? We're just trying to figure out if I can find what's the probability of picking a junior. if a survey participant is selected at random, what is the probability that he is satisfied and a junior? What is the probability that he is satisfied and a junior? $63? Yeah, you all agree with that? How did you know that's perfect? How did you know that was the case? We don't know the probability, we just know the total number right now. So we found the intersection, right? It's an intersection. So I'm looking at, okay, of all the people that are satisfied and all the people that are juniors, this one right here, there are 63 juniors that are satisfied, right? Or there are 63 people that are satisfied that are also juniors, okay? So 63 out of 375, which would be equal to 0.168. So you're about 16%, 17% chance to find a junior that's also satisfied. Just reading the table, right? Just reading that overlap. So the last question says, what is the probability that you pick somebody at random? What is the probability that they are satisfied or a junior? Now is the time where you're looking at some sort of compound event. I can pick somebody who's satisfied, or I can pick somebody that's a junior, right? I have two events going on there. Do they overlap?
No.
Yes, we just saw they did, right? Because you can be a junior and you can be satisfied, right? So they overlap, they are not disjoint, they are not mutually exclusive because they can be in the same category, right? We can have them overlapping, I guess would be a better way. So because we're looking for satisfied or a junior, what operation will I be doing? Will I add? Because we talked about that last time, right? Anytime we say I'm gonna do this or that, that's implying that we're gonna be adding in our probabilities, right? That's our addition rule. Yes, you remember that? Did anybody practice that over the weekend? Uh-oh, we'll practice it, okay? So if we are satisfied or a junior, then we're gonna take the probability of satisfied plus the probability of a junior minus the probability of satisfied and a junior. Because they are overlapping, right? Because they would be double counted. So we can just take our values here. I have 0.621 plus 0.248 minus 0.168, because those were the decimal values, all right? I could have just added the fractions up in the numerator, but ultimately I'm going to find that 0.701 is the result. That's the probability of me finding either someone who is a junior or they're satisfied. It's a 70% chance. Okay? So contingency tables are super easy for us to be able to look at and read probabilities off of. All right? Because what we're doing in essence is really just creating their relative frequencies. Right? We've already done relative frequencies, but what a contingency table does for us, or these two-way tables, what they do for us is they allow for us to be able to see that overlap. So it's clear for us to be able to see from the table that we had above what columns overlap what rows, right? Because you have a single cell that's going to be in both a row and a column, right? And so it's an easy way for us to understand intersections, okay, mathematically. Okay, questions on that? So let's look at an example then where we don't really have the table given to us, but I can create a table. I can create a contingency table to be able to understand the probability a little bit better. So this one says 100 people were asked, do you favor stronger laws on gun control? Of the 33 that answered yes to the question, 14 were male. Of the 67 that answered no to the question, 6 were male. One person is selected at random. What is the probability that the person answered yes or was male? Okay, so when we think about these tables again, they're called a two-way table because I'm comparing two different categories to each other. So what is the one category that I would have here? Do you favor gun control, right? And your responses would be either yes or no. That's what the responses that they're looking for, all right? So I have a yes and no for gun control. And what's the other category that I have? Gender, right? So I have gun control and I have gender. So I'm gonna make this table. We're gonna say gun control answers for yes and no. We're gonna say male and female. So looking at the paragraph up here, it says, of the 33 that answered yes, what do I do with that number? What is that? Of the 33 that answered yes, what would that be? The total, right? So the 33 that we have here ends up going down in this row, column right there, right? So 33 of them answered yes. And what would I do with the 14? Where would I put it?
On the male.
On the male, but where?
On the yes.
Yes, males. That's right. So that would go here. Okay. Of the 67 that answered no, what would I do with that? Where do I put it?
Bottom.
Bottom where?
No.
Bottom of the nose. That's right. 67 here. And what would I do with the next value? What would I fill in next? 6 of them were male. Where does that go?
On the no.
On the nowhere.
Male.
No males. All right. So I have some blanks here though, don't I? What am I going to do here? How will I finish filling this out? How will I know the total number of females that answered yes to stronger gun laws? All right, subtract 33 from 14, and what do you end up with?
19.
Okay, so we can fill that cell in by taking the total and subtracting the males. How about for the no's on the females?
61.
Because we subtracted from 67, that's correct. What does 33 and 67 add up to be? 100. That's right. And so we can come in here and we can also add across for the total number of males. How many males were there? 20. And how many females?
80.
80. That's 20 minus 100 is 80, right? Or you can add up 19 and 61 to verify that that is 80. All right, so before I move on, does everybody understand how we just created this two-way table? We had two categories, right, that we're comparing. One is favoring gun control and one is the gender. Those are the two categories. And then we can create the table based on that. So the probability that we're being asked to look at here says, what is the probability that a randomly selected person answered yes or was male? Yes or male. That implies addition. That implies I'm going to add these things together. In order to do the addition rule, we have to verify, right? We have to take into account, are these events, the probability of answering yes, the probability of a male, are those events disjoint? Are they mutually exclusive? They can overlap, right? Can you not be a male and answer yes? Right? Okay, so that's how we can use this table to figure out what the overlap is. So remember, when we're doing this, we're looking at the probability of someone answering yes, the probability of someone who is a male, minus the probability of yes and a male. So what's the probability of finding someone who answered yes? Give me the fractional value. All right, 33 out of 100. What's the probability of finding someone who was male? 20 out of 100. Does everybody see those values up here? What's the probability that they are yes and a male? 14 out of 100. And that came from the intersection here. Of all the males that were in the thing and of all the people that answered yes, only 14 of them answered yes and were males, right? So I can subtract 33 plus 20 minus 14 ends up being 39, I believe. Or in other words, 0.39. Okay. Now, if you don't add the fractions together, what's the other method you could have done? Change it to a decimal and add them up that way, right? Okay. Change them to a decimal and add them up that way. 0.33 plus 0.2 minus 0.14. All right. I can do those decimals pretty fast in my head. They're 100s. All right. So two-way tables are super convenient when we're trying to identify that component that is the overlap, if we have things that are not mutually exclusive. All right. Okay. So the next thing that we want to talk about then is we can also use another method depending on the way the question is asked. And this is finding something using the complement of an event. So when we think of the complement of an event, it's represented as the probability of the event E with a C up in the superscript spot, right? Raised to like the C power. It's just an indication, it's a notation for us that we're talking about the complement of the event. So the complement of the event, if the green E in my Venn diagram and it represents the probability of an event, then the white area surrounding the green circle is what's left over, right? Yeah? Okay, so if E is the event, if the green circle is the event, then the remaining white square, the area of that white square in essence, is what's left over if you were to cut out the green circle, correct? Okay, so that's the idea behind a complement, because the complement, the white square plus the green circle, has to add up to be what? Which would always have to be what? 100, right? 100%, I should say, or 1. Okay, so if I take the area of the circle and cut it out, I'm left with the complement. All right, so when we find the complement, sometimes it's easier to just say 1, which represents everything there, and subtract off the event. Okay, it's just sometimes a fast way to be able to do things. So if we're looking at the probability of an event that we know, and we would like to determine the probability of the event that does not occur, all right, it's kind of like what doesn't occur, then you subtract it off to find out what's left over. That's the idea behind this. So one of the examples that we can look at here says according to the American Veterinary Medical Association, 31.6% of American households own a dog. What is the probability that a randomly selected household does not own a dog? This is the classic example for a complement. So what's the probability of no dog? That's what we're looking for. The only thing I know is what the probability is if you do have a dog, right? So we're going to take 1 minus the probability of a dog. Because all of those owners who don't have a dog would be left over, right? Okay, so we would have 1 minus. Now, if I took this, since I'm talking about the number 1, I would need to change this into its decimal form, right? Which would be 0.316. And 1 minus that ends up being what? 0.684. So most of the time, if I know the event that does happen, I can use the complement to find the event that doesn't happen, or the part that we don't know. Okay, because there was only two choices here. Either you have the dog or you don't. This is not asking you if you know, what's the probability that you're not a dog owner and you're a cat owner, right? That's not what it's asking. It's simply saying you either had a dog or you don't have a dog. Okay? All right. Any questions on that at all? All right, so the paper that I gave you last time, hopefully you still have that paper. And what I would like for you to do is there are two questions left there, 6 and 7. I would like for you to answer those questions and then we'll go over those answers together, all right? So the paper that I handed out last week, if you don't have it, it's on the back there. And I would like for you to answer those questions 6 and 7 so that we can then go over the answers. Put your calculators out. You don't have them already. Okay, and if you have any questions, you can probably use your neighbor and then you can also ask me.
There's your. So, you know, if you're not sure that. Just straight percentage. No college, right? There's no college there. So that doesn't imply college, right? Don't know. Straight percentages. When you see it, you don't have to. Good if you want to. I didn't. What are you looking for? What's the probability? So no college, right? We'll just make it short. What's the probability that no college? Should we write that down? Capital P for disease no college. So the first percent you have is, and that represents what? So that wouldn't be in college, right? So they're in there. Would you agree? And then what's the next one? What do they represent? Then the next one. So that would be some college.
We got an answer? I'm gonna look over these. You need another minute? I didn't hear anything. You'll need another minute? Okay.
Right.
So what's the complement? All right, let's go over the answers. Okay? Okay, so we're looking at number 6. It says in the question that we're looking for the probability of no college. So the probability of no college would be equal to the very first number that you have in there is talking about 13.4% that did not complete high school, so no high school. If you didn't complete high school, doesn't that imply you didn't complete, that you didn't go to college? Okay, so that would be the probability of no high school. And then the next number in there says 31.9% completed high school. That does not imply, though, that you attended college, right? So probability of high school. Notice how I'm kind of putting in words what it is that they're telling me instead of just going straight for the numbers. Because it's kind of hard to decipher what you're doing if you do that, okay? So my suggestion would be to try to get it into some words when you're looking at it. So these ideas here are just 13.4 plus 31.9% already, which is going to equal what? 45.3? Yes or no? Yeah, is that what y'all got? 45.3%. It's already in percents. All right, let's see if we can tackle the next one. Find the probability that a randomly selected male will be a college graduate. So the probability of college graduate. In the sentence, I know that you did not complete high school, that you completed high school, that you had some college without graduating. Nothing in there is implying that you did graduate, right? So this is where we can take that complement, right? I don't know how many did graduate, but I know how many didn't make it there, right? So this is an example of the complement. So it looks like 100 in this case, because we're talking about percents, 100 minus the probability of no high school, minus the probability of some high school, minus the probability of no college with no grad. Right? You add them up and you subtract from 100, and you should get 38.2%. Okay? So that complement allows us to find the pieces that are unknown. All right? Does anybody have any questions on that so far? So that was without the benefit of a table. You could have made a table if you had wanted to, but we didn't have to in this case. Sometimes you could just read off those probabilities. So then the last one is a table, and this is very similar to the problem that I gave that I worked already. What is the probability of randomly selecting a female? Give it to me. Let me hear you. 0.519. And you got that how, Michaela? What did you divide? Okay, so 62.5. No, 103. I didn't think that was right. 103.7 divided by 200.519. Very good. What is the probability of a college graduate? What is the probability of a college graduate?
78.1. Oh,
78.1 divided by 200.
39.
0.391. I'm just gonna keep it as a decimal because I've already got the decimals. Very good. So the probability of female, the probability of a graduate. What is the probability of a female or a graduate? That is what type of a statement? It's addition, right? Are they mutually exclusive? No, because you can be female and a college graduate, right? So we're gonna take the probability of female plus the probability of graduate minus the probability of female and a graduate. Right, the probability of a female and a graduate was 41.3 over 200, correct? All right. So the total value you get right here would be what, everybody? Good, 0.703. Could you add those probabilities together and subtract off what was in common? All right, you want to make sure that you can get that. Very good. Any questions? No questions on that? This is the addition and the complement rule, okay? So the only other type of probability that we're going to talk about has to do with independence as well as the multiplication rule. And when we think about multiplication, we actually are going to first talk about, and we are specifically only dealing in this class with events that are independent, but we need to define independence. Just like we define mutually exclusive or disjoint, we also need to define independence. All right, independence says that two events are independent if the occurrence of event E does not affect the probability of event F. In other words, your favorite color is blue, you are late for school. So the probability that your favorite color is blue, the probability that you're late for school. Do either of those things does the probability of you having the favorite color of blue affect the probability of you being late for school? No, they're independent of each other. The probability of one thing has no impact on the probability of the other. Let's look at the next one, however. The probability that your favorite hobby is fishing, the probability your car runs out of gas. Oh, I think I read those wrong. Let me back up. Two things that would be independent, although the example I gave is independent for sure. Your favorite color is blue and your favorite hobby is fishing. Should have written down. The probability that your favorite color is blue and the probability that your favorite hobby is fishing are again independent of each other, correct? All right, because one probability does not affect the other. Let's look at the second column over there. You are late for school, your car runs out of gas. The probability that you are late for school, the probability that your car runs out of gas. Do you think that the probability of one has an impact on the other? Technically, if you run out of gas, you're probably going to be late for school, correct? Then those two events, the ones that are on the right-hand column there, are considered they're not considered independent, right? The probability of one thing does, in fact, impact the probability of the other. So that's what we mean when we think about independence, okay? Now, let's look here. Let's go back and let's revisit our rule or let's revisit our probability here. Suppose that we flip a fair coin twice. What is the probability that it will land on heads? Now, if we go all the way back to what we talked about last week and we come up with a sample set, right? What are the possible outcomes that I could have for the probability of suppose we flip it, what is the probability that it lands on heads twice? So if we create our outcome set, I can have a head for the first flip, and I could have a head for the second flip, correct? All right, I could have a head for the first flip, and I could have a tails for the second flip, correct? Or I could have a tail on the first flip and a head for the second flip. Or I could have a tail on the first flip and a tail on the second flip, right? Those are all the possible outcomes of flipping a coin twice. How many total outcomes are there? 4 outcomes. So I'm looking for the probability of a head and a head, correct? Probability of a head and then the probability of another head. And how many ways can that happen? Only 1 out of the 4 times. If I were to just add up, right, the total ways that event can occur, or the number of events that occurred that way out of all the total ways it can occur, correct? Okay, so we have a 1 in 4 chance, or in other words, 0.25, a 25% chance of getting a head and a head. Now, that can get really cumbersome really fast, having to come up with those sample sets and so forth. So another way for us to be able to approach this concept where we have this compound event, more than one thing happening, I'm wanting to know how many times I can get 2 heads. So another way for us to be able to look at that is to say, okay, if I want to know what the probability is for a head and a head, then I can take the probability of getting a head 1 time times the probability of getting a head the second time, because I'm interested in doing this 2 times. We know that if I flip a coin, the probability of getting a head is 1/2, correct? Right? And I would multiply that times the probability of getting a head another time, correct? So 1/2 times 1/2 is, when we multiply straight across, I get 1/4. That's the same answer as I got above, correct? Using the red, the stuff I've written in red right there, where I have to come up with a sample set and look at all the events, all right? That's not always the most efficient way for us to be able to do it. Instead, what we can do is we can use a pattern, right? We can use a formula that says, you know what, if these 2 events are independent, which we're going to go into that just now, if the 2 events are independent, then why don't we just multiply those events together? All right. Now, why do you suppose these 2 events are in fact independent? If I flip a coin and then I flip the coin again, does the probability of the first flip have any impact on the probability of the second flip? So therefore, they are independent of each other, and we can just multiply their events together. Okay? So when 2 events are independent, then the probability of E and F, notice the word I used right there, E and F means I'm going to just multiply their events together. They don't have to be the same event. But as long as they are independent, we would be multiplying their events together. Okay? Flipping a coin and rolling a dice is an example of independent probabilities, right? That are not the same. If I flip a coin and I roll a dice, those are 2 different probabilities depending on what I'm looking for. If I wanted to know an and question, I would just multiply their events together. So and becomes multiplication. What was the key word we were looking for in the previous formula? And what does it imply? Adding. All right, so and is going to imply multiplication in statistics or implies addition in statistics. Okay. All right, here's a fun question. I had to update my picture. My kids would have been mad at me. These are my 3 children. They're not very little anymore, right? Do you notice? That's kind of hard to tell. Did you notice anything about all 3 of those kids? They have red hair. All 3 of my children have red hair, right? Right, Red. Huh? All right, so I obviously don't have red hair, do I? Okay, so what is the probability that all three of my children have red hair? I thought it was just gonna be like a miracle when the third one had red hair. I was like, wow, that's gotta be so rare. Well, it's not exactly as rare as you think it's gonna be. So, do y'all remember, I always forget what this is called. Help me out, biology people. The Yes, what did you call it?
Punnett square.
Punnett square? Yep, that's it. All right. So, my husband had, although he doesn't have red hair anymore, it's all gray, but he had red hair, okay? This is my husband. Me, I had brown hair, but my dad had red hair. All right? So you end up with what? VR, VR, RR, RR, correct? Those are all the possible combinations for the hair gene, right? If I'm explaining that right for my kids. So there's 4 different combinations, right? 4 different possible ways for us to look at them. Now, if I wanted to know, if the question is, what is the probability that all 3 are red-headed? We have to ask ourselves before we go into this, are these events independent? Does the hair, the color of hair of my daughter, who's the oldest, impact the color of hair for the second boy? No, or the third boy, right? So every event is independent. So what is the probability of getting a redheaded child for me? How many ways? So the double R's means that they're going to be redheaded.
It's 50%.
So 2 out of 4, right? Or 1/2, call it 1/2. Times, that's Mackenzie, that's my daughter, times Blaine, times Landon. Multiply across and I get 1 out of 8, which is really a 12.5% chance that all 3 of them had red hair. It wasn't quite as miraculous as I thought, right? It's not unusual, is it? How do we define unusual? Less than 0.5, right? So it's not unusual for me to have had 3 kids with all red hair. Kind of interesting, huh? Yeah, that was when she graduated in May. Really happy for her. Okay, let's look at this. So all we're looking at for in this particular section, this multiplication idea, right? Independence and multiplication. So when we think about independence, independence says that 2 events are independent if one event does not affect the outcome of another. If you're writing this definition down at the top of that paper I handed you, okay? Right, so independent events have to do with the fact that the probability of one event does not affect the probability of another. The multiplication that we use, rule that we use for independent events is simply going to be the probability of event E and F. There's that key word there. If they are independent, then we will multiply the 2 events together. So the last thing that we want to cover, well, let's practice one of those. Another one here. All right. Suppose that a company selects 2 people who work independently inspecting timber. Their job is to identify low quality timber. Suppose that the probability that an inspector does not identify a low quality timber is 20%. They miss it, right? So they're going to miss it about 20% of the time. If they don't identify it, then they're missing it. So the first question says, well, what is the probability that both inspectors did not identify the low quality? So we get a miss and a miss, correct? Isn't that what that is implying? Sometimes it's helpful to write out that you're like, put it in either that and or the or statement to identify, am I fixing to add here or am I going to multiply? So the probability of a miss or not identifying is 0.2 for the first guy times 0.2 for the second guy. Now, before I did that, I should have asked the question, are these two inspectors, are they independent of each other? Generally, they're not the same rank, right? They're not the same person. So therefore, the probability of guy A over here missing something has no impact on the guy over here. They're independent of each other, all right? So yes, I can use our new rule here, and I find out that 0.2 times 0.2 is 0.04. Okay, 0.04. Now, right off the bat, if we were using the 5% of the time would be unusual for something to happen, okay, that's kind of the standard across the board. Would it be unusual for me to have two inspectors miss the low quality timber? It would be, because it's 0.04, right? Or 4%, I should say. So it's unusual for us to have that happen, isn't it? Can you all see that? It would be unusual for us to have this happen. If that was our base, if that was the criteria that we had set. Okay, if we were okay with missing at 90, if we were okay with missing at 5% of the time. All right, now the next question says, how many inspectors should be hired to keep the probability of missing the low quality timber below 1%? So we only want to miss it 1% of the time, right? The stakes just got higher. We want to have a better quality assurance on our product. So we're upping that percentage. We're decreasing it, I guess you should say, right? Or I should say. All right, so how many do you think I need to have? See if you can work that one out on your paper. Just try something. See if you're right. I've got guy 1 over here, he misses it 20% of the time. I got guy 2 over here, he misses it 20% of the time. Combination of those two guys missing it's only 0.404%. How many inspectors do I need to have to keep the probability below 1%? 3. Did you all get 3? Because you just went for it and you multiplied what would happen if I add another guy into it, right? So if I were to say the probability of 3 misses would be 0.2 times 0.2 times 0.2, which is 0.008, which is less than 1%. That's 0.8% if I move the decimal place over. So I would just need to hire one more inspector to make sure that my quality assurance can drop it down, that I'm only going to miss it less than 1% of the time. Okay, can you see how this is an example also? It's kind of previewing of us of when we move forward, how that the unusual value, that 5%, which is a kind of the across the board number that we typically use, doesn't have to be there. That doesn't have to be the number that's chosen. It depends on what you want out of it, okay? And in this case, maybe you want to have a higher quality product than somebody else, for that. So that's how they did that. I want to also point out that I could have taken the 0.2 and raised it to the 3rd power, right? Because that's exponential notation. Exponential notation is shorthand for repeated multiplication, isn't it? So if I am multiplying the same number by itself, like I did here, the 0.2, right? 3 misses, so the probability of a miss 3 times, then all I have to do is take that individual probability and raise it to that power. Yeah? Y'all understand what I'm talking about? Because it becomes 0.2 raised to the 3rd power, which is 0.2 times 0.2 times 0.2. Okay? So that brings us then to this last part here, this at least probability. So when we think of at least probabilities, this is a little wiggle room here, right? If I have something that happens at least once, then it would happen one or more. Think about that. This gets into like backwards thinking or looping thinking sometimes. If I have something that happens at least once, it's going to happen one time or more, correct? So the complement of that would have to be something that never happened. Because at least says it happened one or more. The complement of that is it didn't ever happen. All right. So the probability, let's look at an example here. The probability that a region prone to hurricanes will be hit by a hurricane in any single year is 1 out of 5. 1/5, 20% actually. What is the probability of a hurricane at least once in the next 5 years? What is the probability of a hurricane at least once in the next 5 years? Okay, so let's do some thinking on this one. So if the probability of a hurricane is given to me as 1/5, what is the probability of no hurricane? What's the probability of no hurricane? 4/5, right? Because that would be 1/5 of the time it does happen, 4/5 of the time it doesn't happen, right? 1/5 it does, 4/5 it doesn't. Oh, let me think about this for a second. All right, I'm gonna show it this way. I think I might have a better way to explain it. So we've got some numbers up there, but what I want to show you is, I'm gonna do, and then we'll come back and look at how you don't have to do it this way if you don't want. Sometimes, have y'all ever done a tree diagram on any statistics? Have you ever seen a tree diagram? Anybody? All right. Tree diagrams would be just exactly that, a diagram that's just representing the probability of what we have going on a multi-event. So in a tree diagram, we would have these branches of a tree, all right? And if these branches represent the probability of our event happening, then we have a hurricane here that could happen in a year. And then we have the alternate of that, right? The complement of that would be no hurricane. Do we agree with that at least so far? Okay. And then on the stem of these trees, we write their probabilities down. So the probability we're told for a hurricane happening is 1/5 of the time. The probability for no hurricane, we can surmise, would have to be 4/5 of the time, because each of those branches, right, on this same level have to add to be 1. So all the total probabilities out of these branches on this particular year have to add to be 1. So this is what could happen in year number 1, right? In year number 1, you can either have a hurricane or you could not have a hurricane. Now, let's think about year number 2. Year number 2, I can have a hurricane or no hurricane, or I can have a hurricane and no hurricane, right? So this is year number 2. So let's go back. Let's look at this. So on December 31st, at the end of the year, we had either of these 2 events happen, correct? All right, now we start over. So maybe I'm here on January 1st of the next year? On January 1st of the next year, I could have another hurricane happen or no hurricane happen, right? All right, well, what happened if on January 1st I was here? I could still have a hurricane or no hurricane, right? Yeah? Want me to say it again? Yes or no? Okay, so what we're doing is we're just building a diagram to represent what's happening here. So on December 31st, I could be here on year number 1. And on that next year, I could have either a hurricane that happens or I could have no hurricane that happens, right? Well, what happens if instead of being over here at the end of the year, I'm here? So now I'm starting a new year and I could have a hurricane happen or I could have no hurricane happen, correct? Yeah? Okay, so we have some possibilities here, right? And each of these branches, which are representing the years, right? Year number 1 and then year number 2, all right? So that's how this tree is growing. And I would have 1/5 and 4/5 for the probability of each of those happening as well. I would have 1/5 or 4/5. All right, let's look at year number 3. Year number 3 could have happened hurricane, no hurricane, hurricane, no hurricane, right? Hurricane, no hurricane. And your tree starts to get really big. This would be representative of year 3. And each of those branches has that probability we talked about. And so depending on how you ended the previous year depends on where you're at on the next year, right? You still have, though, a brand new year that's starting out. So you either are here at the hurricane on this side over here, and I know that in this brand new year, I could have a hurricane or I could have no hurricane. Hurricane or no hurricane, right? It just keeps repeating itself and it just can keep getting larger and larger. But what we're trying to identify out of this is the probability that I have at least one hurricane. The probability that I have at least one hurricane. Okay, so let's go back for just a second. If I start here at the beginning of the year, and if I go in this direction, right, I've had a hurricane, right? That's at least one, okay? I could be here, I could be in the second year and I could have a hurricane. I could be over here with the no hurricanes and move in that hurricane route, right? So if I'm looking at this right here, if I have at least one hurricane that occurs, at least one hurricane that occurs, then this branch over here, let me highlight it, then this branch over here that I just circled represents the only branch that has no hurricane, right? That's the only branch that has no hurricane, no hurricane, no hurricane, and I can keep going on. Do you agree? All of this over here represents the probability of at least one hurricane, doesn't it? Because there's at least one hurricane in these possible routes, correct? All right, so what becomes easier on this type of a problem when we're looking at it is, if I want to know what the probability is of at least one hurricane, maybe it would be easier for us to say 1 minus the probability of no hurricane, right? Rather than adding up everything that was not highlighted in yellow, maybe it would be easier to say 1 minus those things that didn't happen. Do you see that? It's the complement, okay? So when I'm thinking of an at least something did happen, the complement is 1 minus it didn't happen. Some people can just click with that, the verbiage, and some people can see a diagram, right? Now, I only represented 3 years here, but if I were to keep going with this tree, I would still only highlight that far right-hand side, correct? So technically, I would have, since I'm looking at 5 years, right? We want to know what is the probability of at least one hurricane in the next 5 years. The probability of at least one hurricane in the next 5 years becomes 1 minus the probability of no hurricane each year. So when we do at least probabilities, we're actually looking at the complement of it not happening, the event not happening. All right. So how do I find this out in my calculator? Well, the first thing, what's the order of operations here? Exponents, right? Exponents. So I'm going to take 4/5. And I am going to raise it to the 5th power. So 4 divided by 5 raised to the 5th power. And then I'm going to subtract that number from 1. So make sure that you can get 0.672. Everybody able to get 0.672? So there's a 67% chance that your region, wherever this is at, is going to be hit by a hurricane at least once in the next 5 years. All right. Now over there in the red, that represents what I've highlighted for 3 years worth of the green. All right. And really, if you just start to see that pattern, some people like it, some people don't. Okay, sometimes tree diagrams help, sometimes they don't. But that explains pictorially what we're talking about when we're using a at least probability. All right. So you have 3 questions there on that paper that I gave you. See if you can answer those 3 questions. Before we have to leave. Okay, and if you need help on your calculators, let me know while you're here so I can help you. Oh, there it is. The little carrot, the little house, the little symbol right there. Right, so that's our exponent. So if I did 2 that would be 8, right? Yeah, that's the symbol we want. One minus that. remember that when we're thinking about at least probability, that the complement of an at least is that the event never happened.